Hey, it's Linford here, and today we're going to be talking about the topic of synthetic division. As you can probably tell, I'm a bit under the weather, but I wanted to make a video to share with you this really cool process for performing division of polynomials. Now, previously, we could only perform division using the long, elaborate process of polynomial long division. And that's fine, but it's a bit tedious, it's a bit time-consuming. Today what we're going to do is we're going to explore what synthetic division is, we're going to look at the requirements for it, what the process is, do a little bit of practice problems, and really see how much of a shortcut and how quicker of a process this is than regular polynomial long division. Okay, so the rationale for synthetic division is really just being a shortcut to polynomial division. And what this is going to do is it's going to make a very quick, expedited process for figuring out what the quotient and remainder of two polynomials are. However, this is all fine, it's fantastic, it's really helpful, but it only works in certain cases. So synthetic division is just a process that we really have to be careful when we're using. It's great and all, but it only is going to work when the divisor, and remember that's the thing we're dividing by, so the divisor must be of the form x minus r. Oh my gosh, my voice is terrible. Must be of the form x minus r, where r is a constant number. So what we're saying here is that what you're dividing by, that divisor, must be x minus a number. And it must fit that form exactly. So we need things kind of like x minus 2, x minus 5, things like that. What we don't want is x squared minus 2. This does not fit our form, okay? We want a degree of 1. This has a degree of 2. So therefore, that divisor would not work. Similarly, if I had something like x cubed minus 3 or 2x minus 4, these do not fit the form that we want, so we could not use synthetic division on this, okay? We're only going to use synthetic division where we literally have x minus a number, or we can write it in that form. So let's try a practice problem here, and let's go over the process as we go through this problem. Now, it's a bit of an elaborate process, so what I want us to do is really look at how it's set up first, and then try to see if we can make a step-by-step process for how to do this. The first thing I like us to do is always make sure your polynomials are in descending order. And by descending order, we mean the exponents drop by 1 every single time. So we start with the highest exponent and go down to the smallest exponent. And sure enough, we are in descending order. Now, what we then want to do is figure out what our r is. I always like to write this on the side just so I can remind myself. Now, oftentimes students would say r is negative 2 because I have x and I have a negative 2. But in fact, r is really positive 2. And the reason for that is, well, what is the number we're subtracting from x? Well, I'm subtracting 2 from x. I'm not subtracting negative 2. So r here in this case is going to be 2. So here's how we set up synthetic division. We're going to set it up in this kind of chart format, I guess you can think of it as. Try and follow along. We're going to first put the r on one side, and I'm going to make this kind of sideways L shape, almost like a chart. And what I'm then going to do is I'm going to put in a row of coefficients from the dividend. All the coefficients you see here came from the dividend. We had the 3. We had the negative 14. Remember to include the signs. And we had the negative 10. Okay, now that we have the coefficients in place, and you'll notice I left a bit of space here. That's okay. We're going to use that space. What we're now going to do is really replicate the process of long division, but we're only going to do it with the numbers. So here's how this process works. We first take the leading term, which is the 3, and we bring it down. So I draw a little arrow, and I write 3 on the bottom of the chart. What I'm then going to do is I'm going to take the 2 and multiply it by 3 to get 6. When I have this, I'm now going to add these together and get -8. And I'm going to keep doing this process of multiplying the bottom value and adding these values. And I'm going to do that until I run out of terms. So let's do this one more time. 2 times -8 is -16. Let's add this together. And we end up with -26. All right, so we ran out of terms, and we have these 3 values here, 3, -8, and -26. Do me a favor and put like a little half box around the -26. This number is going to be our remainder. Just like in long division, the last thing we got was our remainder. This is what our remainder is here in synthetic division. And right away, we have our answer. Our answer is made up of these coefficients. Let me show you how we write that answer. We're going to take the first coefficient, 3. We're going to put an x on it, and we're going to have 1 degree less than what we started with. So since we started with an x squared, we're now going to have an x to the first. Then the next coefficient is -8, and its x value is going to have 1 degree less than this, which would be x to the 0. But x to the 0 is just 1, so don't even bother writing it. So our answer is 3x minus 8, and then we have our remainder. Remember, we write our remainder the same way. We're going to put that as the minus 26 over x minus 2. We write the remainder over the divisor. And there is our final solution. So let's remind ourselves of what this process was. We first have to make sure we're in descending order. That's super important. We then want to figure out what the R value is and just get a general setup of that little chart. Then we get into the process. Drop down the first term. That's super important. We dropped down the first term. We just carried it down. So that 3 came right down, and that's the first part of our answer. We then multiply that value by R. So we took that 3, we multiplied it by 2 to get 6. So that's what we're writing up here. Everything we write up in this space is what we multiplied 2 by. Once we did that multiplication, we then added that value to the next coefficient. So that's what we're doing right here. All of these values are the sums of these columns. And then we just keep this process going. We continue this process until we run out of terms. The big thing to remember is that that final value is your remainder. So we kept this process going of multiplying to get this, adding to get this, and we kept that going until we reached the very end and we found what our remainder was. Now you might want to put a note to yourself that when you are writing your solution, you go ahead and you attach the same variables, but they're going to be 1 degree less than what you started with. So that was to the first, that was to the 0. The reason that this is 1 degree less is because we're dividing by a degree 1 polynomial. There's a little bit of more technical explanation to that. If you're curious why and want to talk about that a little more, please feel free to email me. But let's go ahead and practice this process a little more. First thing that we want to do, make sure we're in descending order. And in fact, we are. Now let's identify the r. The r in this case is 6. Now that we have that, let's set up our chart. We have 6. I'm going to set the chart up. I'm going to put in the coefficients. The coefficients of the dividend are 1. Remember, there's an imaginary 1 there. -4. And a -12. The first thing we want to do in our process is bring down the 1. We're now going to multiply 6 and 1 to get 6. We're going to add 6 and -4 to get 2. We're going to multiply 6 and 2 to get 12. And we're going to add -12 and 12 to get 0. And again, put that little half box around there. All right, well, now we have our solution. Our value is, the first coefficient is 1. And we're going to have x to the 1 degree less. So it's going to be x to the first. I'm going to add 2 x to the 0 plus a remainder of 0. I don't need to worry about that. It divides unevenly. So my solution, without all this unnecessary stuff, is just x plus 2. That is a lot faster than if we had to do polynomial long division on this. So hopefully you're starting to get this idea of this repeated multiplication and adding, and hopefully you're seeing how we're setting up the final solution with our x's. All right, what I'd like you to do is pause the video, take a couple minutes, and try this problem out for yourself. See, can we perform synthetic division on this? And then if we can, go ahead and give it a try. All right, well, hopefully you had some time to work on this. But the big question is, can we perform synthetic division on this? Well, the first thing we have to do is look at our dividend and see, is it in descending order? Well, it's really not in descending order, so let's put it in descending order. We have z cubed minus 2z squared plus 2z minus 5 divided by z plus 3. Okay, you're probably noticing a couple red flags that are going on here. One thing in particular is that we have this z plus 3 as our divisor. Now that should be a big warning to us because wait a minute, our rule for synthetic division said that we had to have the variable minus a number. So we have this case the variable plus a number. That doesn't seem like it should be allowed. What I would have liked is z minus 3. But in this case, I have z plus 3. So can we perform synthetic division on this? Well, remember, I worded it very carefully at the beginning, and I was a little tricky about it. I said that we always wanted to have the variable minus a number, or we wanted to be able to write it in that way. So is there a way I could write z minus some number and have it be the same as z plus 3? Let's pause the video for just another 30 seconds, and let's see if we can think about a way of setting this up. Okay, hopefully you noticed a little bit of the trick, but what if, instead of writing z plus 3, I wrote z minus -3? I never said r had to be a positive number. In fact, r could be any number, positive or negative. So z plus 3 is the same as z minus a -3. So technically, since we could write this divisor in the form of the variable minus a number, we can perform synthetic division on this. This is okay to do synthetic division on, and we can go ahead and get started. Now, the first thing we want to do is make sure we know what r is. In this case, r is going to be -3. What number are we subtracting? That's -3. So, nothing different. We just have a negative number now. Let's set this up like before. -3. I'm going to get my little chart going. What are my coefficients from the dividend? We have 1 for the z cubed, -2 for the z squared, positive 2 for the z to the first, and negative 5 as our constant. All right, the process starts by dropping 1 down, multiplying by negative 3, adding to get negative 5, multiplying to get positive 15. Again, be careful with your signs. Double negatives makes a positive. And then adding to get 17. Now let's see, 17 times negative 3 is going to be negative 51. So when we add these together, we get a negative 56. Box that answer. That's our remainder. And we very quickly have our solution. So our answer is going to be 1 z to the second, because we drop 1 from what we started with. Since we started with the z cubed, our answer is going to be z to the second minus 5z plus 17 minus the remainder of 56 over the divisor z plus 3. And that, oops, don't want to cross out the answer. That will be our final solution. We have the z squared, we got the negative 5 attached to the z, we got our 17 in there, and then we're subtracting the remainder over the divisor. This fits our form of Euclidean division, and it makes for a very quick process. All right, let's try this again. I want you to pause the video and try and see if you can perform this division. Notice that we do have a little sign change here like we had before. Nothing too worrisome, but see if you can perform a synthetic division on this. All right, well, hopefully you had plenty of time to get this problem figured out. But one of the things I think you might have noticed right from the get-go is, yes, it's not in descending order, but when we put it in descending order, we're going to notice that we are kind of missing a term. We don't have anything with an x squared, right? There's no x squared in there. It's kind of disappeared. We're wondering, well, what do we do about that? Because every time before, we were going down 1 each time. Well, we actually do need an x squared in there. It actually is vital that we have an x squared in there to perform our division. So, Linford, what do we do about this? There's no x squared, but we need it in there. Can we not perform synthetic division on this? Well, fear not. It turns out we actually can. And it's a very simple trick, same trick we did with polynomial long division. If there's no x squared in there, put 1 in. What do you know? If I put a 0x squared in there, well, that's just 0, but hey, it's a little placeholder. I have an x squared in there. Its coefficient's just 0. It's not really going to do anything, but it's still in there, and it's going to make the process work much easier. So I can go ahead, throw that placeholder in, and then let's get to setting up our chart. Now in this case, r is going to be negative 3. You can think of that r as always being the opposite sign. So r is negative 3. And the values we're going to plug in are 1 for the x to the 4th, 4 for the x cubed, 0 for the x squared, 5 for x to the 1st, and negative 6 as the constant. All right, really try to get this process down of how we're going to do this. Because once you have it down, it's going to make your work much, much quicker and easier. First thing we do is we bring down the 1. Oop, my stylus is running out. We bring down the 1. We're going to multiply that 1 by negative 3. Then we're going to add that to the 4 to get 1. We're then going to multiply that by negative 3 to get negative 3 again. Add this to the 0 to get negative 3. Multiply negative 3 and negative 3 to get positive 9. Please be careful with your signs. We're then going to add 5 and 9 to get 14. Multiply it by negative 3 to get negative 42. Add these together to get negative 48. That's our remainder. So let's go ahead and write our final solution. Let's see. We got a 1x cubed. Again, 1 degree less than what we started with. we have a 1x squared, a negative 3x, a positive 14, and then we're going to subtract our remainder of 48 over the divisor of x plus 3. And that will be our final solution. Now, this really wouldn't have come together if we didn't put in that little placeholder of 0. Because if we didn't put that in, we would actually be kind of doing work a little backwards. I would have been adding 5 and negative 3, and I would have gotten a totally different answer. So including that placeholder was incredibly vital to the problem. I'd put a note to yourself on there to make sure you include placeholders for any of those missing terms. All right, now that we know all about placeholders, now that we're comfortable identifying what R is, try this last problem out, see if you can figure it out, and then we'll come back together in a little bit and see what the final solution is. All right, so we're going to go ahead and try to figure out this problem. We need to follow our process and make sure that we are totally set with how to go through this step by step. First up, make sure we're in descending order, and make sure if we need placeholders that we put them in. In this problem, we very obviously need placeholders. So here's what we're going to do. I'm going to put a p to the 4th plus a 0 p to the 3rd plus a 0 p to the 2nd plus a 0 p to the 1st minus 81. This polynomial is no different than what we originally had with p to the 4 minus 81. All these zeros just cancel right out. But going ahead and actually writing them out makes it a lot easier and possible to perform our division. So let's identify what our R is. R is going to be positive 3. So I'm going to set my chart up. Got the R. And then here are our coefficients. We got quite a bit of them. We have a 1 for p to the 4th, 0 for p to the 3rd, 0 for p squared, 0 for the p to the 1st, and negative 81 is our constant. All right, the process is bring down the negative 1, multiply it by 3, add it to 0 to get 3, multiply to get 9, add it to 0 to get 9, multiply by 3 to get 27, add it to 0 to get 27, multiply it to 3 to get, 81, add that to negative 81 to get 0. That is our remainder. So this remainder of 0 means that this polynomial goes in evenly to this polynomial. It's actually factorable. So our final answer is going to be a 1 p to the 3rd plus 3 p squared plus 9p plus 27. And that is what polynomial multiplies by p to the negative 3 to get p to the 4th minus 81. So hopefully you're seeing this very quick, very shortcut process to perform division. Again, remember it only works in special circumstances. And I'm kind of being a little facetious with my language. Actually, there's a way of doing synthetic division with other types of polynomials. In fact, there's a way of doing it with divisors that don't look like a variable minus a number, but they get a little more elaborate, and really, I don't think they're any easier than just doing polynomial long division. If you'd like to see some of those methods, feel free to send me an email. I'm happy to show you. But for the most part, this process is going to make taking tests much quicker, and really when we try to find things that are factorable, finding out what those factors are much quicker as well. Again, if you have any questions or comments, feel free to send me an email. My email address is klinford@wccnet.edu. Thank you for all the views and all the likes. I really appreciate that. And thank you for putting up with my very poor voice right now. I'm glad it lasted for this video, but I'm starting to lose it, so I'll end this video now. Thanks, and I'll see you again next time.